Okay, so here's our second ANOVA example. In this one, I'm going to imagine that um, we're comparing three swimmers and we want to choose which one is the fastest, like maybe to be like our representative in a competition or the fourth member of a relay team or something like that. Now, in something like the US Olympic trials, what they would do is have one race and see who wins, and that's the person who makes the team. Or if like three are going to make the team, then the top three out of all the racers make the team. Now, a lot of countries don't do it that way. They don't make it down to one race because what if their best racer just happens to have a bad day and then they don't make the Olympics? Um, that might not be the best choice if you're trying to put together the strongest team possible. So what a lot of other countries do is they look at each racer's like sort of record over the entire previous 6 months or year, and then try to like make a judgment based on their recent career. So lots of different races are factored in. So let's say that we want to do something more like that, and we give each racer a chance to run their race 5 times. And so these numbers are supposed to be in seconds. So each swimmer repeats the race 5 times. Their times are below in this table in seconds. So who's the fastest? Like at first glance, it looks like swimmer one is the fastest. They're the only one who ever went under 114 seconds. They did that 3 times. They had one slow race that tied swimmer two's best race and was worse than all the races by swimmer three. So I think that swimmer two is probably out of this because every single race they did was worse than every single race that swimmer three did. And they only tied the worst race of swimmer one. So swimmer two is probably almost certainly out of this. But what about between swimmer one and three? Swimmer one had 3 races that were better than anything swimmer three did. But they had one race which was worse than everything that swimmer three did. So how do we decide between the two of them? Well, I guess it's like if I'm going to do a statistical analysis that includes all 3, my only choice is ANOVA. Or I could say, well, swimmer 2 is definitely out. They sort of didn't really demonstrate that they're competitive with 1 and 3, and so we could just do a two-group comparison between 1 and 3 using our sort of like more detailed tests that we did earlier, like a few days ago. But let's run a test with all 3 of these. So I'm going to copy these over to Minitab, and let's just put them in the same table over to the side. So this time I knew I had headers, so I clicked it in the header section and got my headers up there. So let's run an ANOVA test comparing swimmers 1, 2, and 3, even though I know that swimmers 2 is probably out of it. So ANOVA, one way. We'll get rid of these numbers from example 1. We're going to compare swimmer 1, 2, and 3. Let's see what we get. Okay, so we got a p-value 0.01. So that's less than 5%. So maybe we do have a statistically significant difference. Our confidence interval for swimmer 1 is from like 109 to 118. For swimmer 2, it's 118 to 125, which is basically completely worse than both swimmer 1 and swimmer 3. They both like their high end was low 118s, and swimmer 2's low end was 118 and higher than the sort of the bad end of swimmer 1 and 3. So swimmer 2 is definitely, their confidence interval is completely separate. But there is actually a fair amount of overlap between swimmer 1 and swimmer 3. So you can see that like swimmer 2, like their bar does not really overlap with 1 and 3. So 1 and 3 overlap with each other. It's possible that they have the same mean, but swimmer 2 is totally out of it. Okay, so we got a small p-value. We're saying that we're rejecting the null hypothesis. We do not think that they're all equal. But visually, it looks like the way that they're not equal is that swimmer 2 is definitely slower. And maybe we don't actually know that there's a difference between 1 and 3. we would have to run another test. Maybe we should do that. So the ANOVA test said that there is a difference, but it looks like maybe the difference is that swimmer 2 is just smaller. And you can see that the way that this graph looks different than the graph we had for the roots is here, all the bars kind of overlapped with each other, and there was numbers that look like they could reasonably be part of all three intervals. But now the bottom of this middle one is sort of like, doesn't quite overlap with the tops of the other two. So there isn't really a number that hits all three bars. You can hit the bottom two, you can hit the top one, but you can't hit all three of them at the same time. So if I'm going to try to distinguish between swimmer 1 and swimmer 3, then I would have to rerun it with just swimmer 1 and 3. And now I could use a 2-sample t-test comparing just swimmer 1 and 3. So we'll put swimmer 1 in sample 1, swimmer 3 in sample 2, and I'll use my regular alternative hypothesis of not equals and see what I get there. And so now I'm getting a p-value 0.23. So that means that I don't have enough evidence that there's a difference between swimmer 1 and swimmer 3. As far as I know, it's possible that they're still equal, and swimmer 1 just happened to crank out a couple good runs that actually on average they're no better than swimmer 3. So in order to decide, I would have to basically have them do a few more swims as some kind of tiebreaker until we could distinguish which one was actually faster. Okay, so so ANOVA did detect that there was a difference, but the difference it found was not, it didn't fit the purpose of us running the test. We wanted to know if there was one swimmer who was faster than the others and who it was, but all it actually really detected was that there was one swimmer slower than the other two, and as far as we know, the other two are tied. So ANOVA can find a difference, but it could be any kind of difference. So it's very limited in terms of how much stuff it can detect. All right, so I have one more example after this, so we'll stop this one and then move on to our last video.